So for today's video, what I'd like to take a look at, you guys, is being able to multiply radical binomials, and specifically how that's going to help us solve some of the more complicated problems we'll see in this part of the chapter, which is when we have to rationalize when there's a radical stuck in our denominator, but it's attached to a binomial. So we've talked about this rule before, being able to multiply these so that if you have the root of x times the root of y, you can get the square root of the product. All right, so some examples you might see that of like, okay, so what's root 2 times root 3, you would ask? Well, it's root 6. What happens if I start doing stuff like root 3 times root 15, and then we get root 45, and isn't that something I can simplify? Well, it sure is, and we would do that. So it's possible that we, in the process of multiplying two things that cannot simplify, I will get something that can. That's absolutely possible. You might be saying, so what happens if it's something like this, Mr. Card? To which I would say, the associative property of multiplication says this is just 2 times this piece times this piece. So it's just 2 root 6. This brings up the idea of like terms, that I can multiply these together. But when you find yourself with something like 2 root 2 plus 2 root 3, there's nothing I can do there. But when I have like 3 root 2 plus 2 root 2, if we consider these like variables, okay, like terms, I can total those. So those are things that we want to keep in mind as we move into the next part of this lesson. Right? So basically what we've been practicing with is the idea of, can we FOIL, can we distribute something like this? And I do want to point out that you can be using the table method that we've gotten accustomed to using here as well. Normally we're working backwards, trying to fill in the pieces of the table here and figure out what goes up here. But here I know I have a root 5, I have a 2. I have a root 5, I have a negative 4. Root 5 times root 5 is the square root of 25. Oh, hey, that works out great because that cancels. That's a perfect square. 5. And 2 times negative 4 is negative 8. So those are going to be like terms. 2 times root 5 is 2 root 5. And negative 4 times root 5 is negative 4 root 5. Now, these aren't always going to be like terms. It just happens that I have a root 5 in both. Like this could have been root 11, and then this would be 2 root 11. I couldn't add them, but this time I can, so I will. So here's an important possibility that we need to keep in mind. Difference of squares. My favorite example of this is the simplest. X squared minus 4. How can we get x squared minus 4? It's by using the difference of the two. It's by saying x and a positive 2, x and a negative 2. Because this will produce the x squared that I wanted. This will produce the negative 4 that I wanted. And this will produce the canceling of these two pieces, which I also wanted. I don't want any middle term. I don't want it. And I don't get it. It cancels. It's gone. So I can use this and keep this in the back of my mind for when we run into problems where we need to rationalize the denominator, but it's not just a root. It's like something plus the root or something minus the root. So how do we fix that? Using that opposite. So let me show you what I mean. Okay. Normally you might say, all right, Mr. Carr, do you want me to get rid of this square root down here? Well, why don't I just do this? This is what you've been telling me to do. Right. Oops. And this is what you've been telling me to do, is to multiply by the root over the root, because that really simplifies to 1 And so nothing really changes. So on top I get 4 root 5. And then here, well, negative root 5, or so, root 5 here times root 5, that's 5. So I'd have minus 5. And then root 5 times 3, oh no. I took one step forward, and I canceled out this square root, but I added one right here. So I haven't actually simplified anything. So this is where we use this idea of the difference of squares to say, oh, okay, you know what might work? As if I multiply by 3 plus root 5. So let's almost set up like a table method here so I can prove my point. 3 and a positive root 5. 3 and a negative root 5. 3 times 3 is 9. 3 times root 5 is 3 root 5. 3 times negative root 5 is negative 3 root 5. And look at that. 3 plus negative 3, those will cancel. And when I do root 5 times negative root 5, that's negative root 25, otherwise known as negative 5. So I've completely eliminated any square root symbols, and 9 minus 5 is 4. So I would just say, all right, the whole thing's just over 4. I've totally eliminated any roots. I just got to worry about what happens up here. 4 times 3 is 12. 4 times root 5 is 4 root 5. And this happens to be one that I can actually simplify. 12, 4, and 4 are all divisible by 4. So this will really just be 3 plus root 5 over 1, or just 3 plus root 5. Let's try another one here. This time I'd say, all right, I want to multiply by the opposite of this, which will be a negative. So let me walk through this here. All right, let me do the numerator first. 2 times negative 3, negative 6. 2 times negative 5, negative 2 root 5. And the more of these we do, the better we'll start getting at the pattern where like we kind of know that it's going to cancel. I mean, that's why we're doing this, right? Negative 3 times negative 3 is positive 9. This is going to be, okay, root 5, so negative 3 root 5. This is going to be negative root 5. So negative times negative is a positive 3 root 5. So what happens here? They cancel. And then I'm going to get the same thing here last time. Okay. Minus 5 is 4. And again, I just see, can I simplify? Oh yeah, all these are divisible by 2 at least. So negative 3 plus root 5 over 2. And with that, we've learned some of the most complicated ways that we can work with radicals. If you can do this stuff, you're in really, really good shape.